Good afternoon, everybody, and welcome to what I expect to be my least accessible talk ever. You're all probably in the wrong room. I am Titus Winters. I am Google's C++ libraries lead and chair of WG21's Library Evolution Working Group. And I'm going to talk today about the refactoring impact of higher-level design features. As with many Titus talks, I'm going to start with a little bit of historical context. Ground rules, general note. I'm perfectly happy for this to be interactive. If you have questions, don't hesitate to get up and come over to the microphone to ask your question. There's I think, plenty of Slack in the presentation. And I'm almost positive that there are plenty of things that will be not entirely obvious. So if I'm going too fast, feel free to ask questions, okay? But we'll start in the past, in the long, long ago. In the beginning, all code was basically just a mess. The first couple decades of computer programming, code was effectively just a pile, right? You see this in old code that relies on goto everywhere, or programming languages that are based on line numbers preceding every statement, right? We hadn't learned yet, unsurprisingly, that it's easier to read and write and maintain code that structurally enforces some invariance. What values are in memory, what values are in registers, how to call a function, what variables are in scope, right? These sorts of invariants that make it much easier for you to reason about your code. And so over time, there started becoming a push for what was called structured programming. This started roughly in the 50s and came to so completely dominate the programming landscape by the late 80s that we don't really even talk about it anymore. It's sort of assumed. And in the move from a big pile of code to structured programming, we moved to having structures. We moved to having functions with well-defined signatures and well-defined ways that you call them. We went to having loops and conditionals. This is the movement that gave us goto considered harmful. It's not a moral judgment about goto, it's that the structures that are capable of replacing goto give us invariants that make it much easier for us to reason about code. It gives us the ability to locally reason about what is going on, which is critical to scaling into larger and larger software. I can't easily modify a function to take an additional parameter if I have to know what is in a given register at every possible call site everywhere in my code base, right? That's going to be a very hard, add a new default parameter, right? So the move to structured programming, inherently took us out of the chaos and gave us structures and local invariants so that we can think about things. So you could summarize the first 30 or 40 years of programming in a sort of counterintuitive way. By adding additional constraints and structure on how you write code, limiting the types of things that you write, it actually gave us greater flexibility to write bigger and more expressive programs. And thus, having gotten a taste for it, we started extending that set of structures, right? We went from just functions and conditionals and things like that into object-oriented world, giving us classes, and with C++ we started having templates, and now with C++20 we have concepts, and I suspect that this is not the end of that progression. The motivation for this talk is that I said a few months ago in a committee meeting, offhandedly I guess, that types are harder to refactor than functions, and that templates are harder to refactor than types, and that concepts are impossible. And a bunch of people on the committee, very smart people on the committee that I respect deeply, didn't understand inherently what I meant by that. So I'm going to bore you for an hour with what this means, okay? But in order to explain why these higher level, this progression into higher level structures, in order to explain why that is increasingly difficult to refactor, I have to also explain what I mean when we at Google talk about refactoring. Hence, what do we mean by refactoring? And a lot of people, when we say refactoring, are thinking of effectively the Fowler Refactorings, right? Martin Fowler published a great book a couple decades ago on like refactoring basic. He came up with sort of an initial list of these are the sorts of changes that you might want to make to a program. The Fowler Refactorings are the types of things that you might find in an IDE in a little refactoring menu. You might say, highlight a block of code in the function, go to your IDE, hit refactor, extract function. And it's going to pull that block of code into a new function. You give it a name, and it figures out which variables are coming in and out, and figures out how to pass those variables to that function. And congratulations, you've done a refactoring. Other things from refactoring.com/catalog, you might inline or outline a function. You might replace magic literals and string constants, things like that. There's a whole list of these that goes on for several pages. I would describe all of this model as single-step refactoring, right? The model that most people understand is I'm going to generate a set of changes and commit that change in one step. And here I'm going to admit the terminology becomes difficult and annoying, and the terminology here is a work in progress. I have for a while been talking about atomic and non-atomic refactoring, and I'm trying to move away from that in this talk, so this is the first time that I'm trying this new terminology. The trouble is, we have been talking about atomic refactoring or single-step refactoring using the model from version control, right? An atomic commit to your version control system, an atomic commit to your code base, atomic commit to your repository, right, is all of the things that you can do in one step, right? Which is great. So you can do all of the Fowler refactorings. If you can find every caller to your function, you could change the behavior of your function however you want, because you can make all of those callers acceptant of that change. You could add a default parameter. That's nice and easy. Everyone understands that. You could potentially even do a global find replace for an API, right? You go find everywhere that we spell stood string and you change it to some other name, right? Find replace, no problem. But my question is, are these sorts of changes what you're trying to achieve or how you achieve it, right? What is really the basic unit of change? And I would argue that some of these are kind of how you draw an owl, right? Like, there's a lot of messy details in there in some instances, right? There's simpler, more basic pieces available because this list has kind of a mix of circles and owls in what I think, and what are commonly described as sort of basic refactorings. Some of these are definitely, like, I could change one or two files. Right? I can add a default parameter. I'm gonna edit a header or a header and a CC, right? That's fine. And some of them are going to scale with how much usage there is of the interface in question, right? If I'm doing a find replace for vector, I need to find every place in my project that actually spells out vector. Does that make sense? Right? There's a difference in scale there. Those refactorings that scale with usage have different risks when we rely on those exclusively, right? If that is the only thing in our toolbox, then we are reliant on the fact that we never have to do anything so big that that becomes infeasible. And so we should consider these larger scale sorts of things separately. And the scale issue comes up for several different reasons. You're going to need a more complex refactoring strategy if you have any of the following. Right? If you're trying to make a change across organizational or repository boundaries, say you implement a standard library and you don't see all of the users of your standard library, right? You're going to have to rely on harder refactorings because you can't just do a global find replace. Make sense? Google's issue comes from a different sort of scale problem, which is there's many times that we want to refactor something and it touches more files than we can commit to version control in one step, right? If we were to do, a find replace on vector, that's going to touch hundreds of thousands of files. Well, maybe not 100, but way more files than we can commit in a single step. And that's not actually even a limitation of the version control system, it's a limitation of the usage of the version control system. Right? Hiram and I have both given talks where we've mentioned this sort of inherent limit on your code base and your organization of how many files can you have in a change and submit it in one step, because there's a constant background rate of people also modifying the code base, right? What is the average time between change for a file, right? Can you sync to trunk? Can you sync to head before someone has modified a file that you're touching, right? And even if you manage to pull that off, will you be able to roll it back in the event that you made that change incorrectly, right? Landing a single change that touches hundreds or thousands or tens of thousands of files at once, even if you're technically capable of doing it, is probably not smart, right? You probably don't want to be betting on that as a reliable strategy on a regular basis. You can also get into this if you have contracts about how long a given API is going to exist for, right? It's not unheard of in our industry. I think all of these basically boil down to two primary forms. Scale, or your ability to, how many files can you touch, or if you're an organization that has multiple Git repos, but you don't have any ability to atomically commit to both repos, right, then you're going to have this type of problem, right? If you have APIs defined in one repo and callers in another, you're in the same sort of boat. But then the harder problem is visibility, right? Most people that are going to benefit from the sorts of techniques that I'm describing in this talk are going to get into it not because of version control sync or Google's scale problems, but because of problems more like the standard library, right? You've released an interface, and you don't know where all of the users are, right? They might be private repos, they might be open source, they might be all sorts of things, right? But you have no reason to believe that you can track all of them down, right? You've released it into the world, and now it's out there, right? Tool-assisted refactoring can get you a long way in doing operations in that sort of environment. This is what Absale is sort of predicated on, but it is meaningfully harder to be like, I'm going to throw a tool over the wall to fix whatever problem I have caused. Good luck. Like, it's definitely doable, but the long tail on ways that that can go wrong is fairly long. Because of that difficulty and because of our increasing dependency trees, I sort of abstractly, as a side note, I think the next decade is going to see a lot of progress on sharing web APIs where providers can say, I'm going to make this change. Is this going to break you? Have your CI systems and unit tests execute with that potential change and feed back to you yes or no, right? Without necessarily sharing your code, things like that. Or at least I'd like to see us move that way. We'll see if that actually comes to pass. But in any case, if you have scale problems or visibility problems that prevent you from just changing your API sources and users in a single step, then you're going to need something more than this single-step refactoring mindset. And so I guess we call that multi-step refactoring. This is the idea of executing a large or distributed set of change in a series of steps so that the ecosystem continues to build and function cleanly at every individual point in time, but each step is small enough to be handled as part of the normal developer workflow. Most steps in this process, if you're doing it well, don't need to be sequenced in any particular way. Usually this is going to be introduce a new API, find all of the callers of the old API and convert them individually with no dependency between how they convert, and then clean up, right? So there's minor sequencing between those two things, but it's basically 3 phases. And the phase in the middle should largely be completely independent. And so if we look, what are the things that we might rely on for multi-step refactoring? And I would say that the basic atoms here are of a different sort of flavor than the things that you see in a Fowler refactoring, right? I could add an overload. I know that that's going to be fine. I know that I can do that locally. I can add an alias. I know that that's going to be fine. I know I can do that locally. I can change a caller from one function to another. That's local. I can change an instantiation from one type to another. That's local-ish. I can remove an unused API, right? That requires global knowledge and some synchronization, but can be done with only modifying a couple files at a time. All of these are very nice atoms to base your refactoring strategies on because they can be done while editing a constant number of files, like 1 or 2 files in most cases. Other operations might be atoms, I don't know. In some scenarios, renaming a type, like the stood vector example, could still be considered atomic if the usage of vector is small enough that you can do that as a single step, right? And so these sort of have a different flavor. Renaming a type, changing a function signature, right? These inherently have a larger atom size, or maybe they're molecules. I don't know. Like, we're working out the terminology as we go here. But if you're looking into multi-step refactoring, especially for Google sorts of reasons, just because you have a big scale problem, these are the ones that you're going to lose access to early on. So let's look through some examples. For instance, we needed to rename a type. We had a string piece. That was the original impetus for the proposal that eventually became string view. And internally, during the delta between string view being accepted and us actually moving to C++17, we also implemented this in Absail as Absail string view. So we wanted to rename all of the usage in our code base from string piece to string view. Because of scale, we couldn't use rename the type as an atom. There were tens of thousands of files that referred to this name. So obviously, this is not really going to be a whole hour-long talk. All you do is you copy the body of the class and you put it in the new namespace, right? And you're fine, right? It's easy peasy. Obviously not. There are so many details that go wrong if you do this without thinking about it. So I will go through some of the ways that this goes wrong. For instance, I said before, a multi-step refactoring is going to be much smoother, much easier, if you can do it in such a way that when you're updating callers, you don't have dependencies in which of them gets updated first, right? So I don't want it to be the case that foo.h and bar.cc have to be refactored to use the new type at the same time, right? I would like it if whatever strategy, whatever refactoring plan I have, I could replace string piece with string view in either of these first or both of them at the same time, right? That's going to be a much easier refactoring. But if I do this naively and just touch bar first, this is not going to work because those are two completely different classes, right? So maybe we just write conversions between each other, right? So I could write a conversion so that string view converts from string piece or vice versa. But that fails if you have any users in your code base that have user-defined conversions to your type, right? Because you can't do 2 steps of user-defined conversions. So even if we tracked down, or even if we added conversions between string piece and string view, this user-defined conversion is going to fail, right? Or is going to make our refactoring more difficult. So I guess what we do is we first track down all of the places that there's a user-defined conversion and make it convert to both, but then that fails if you have an overload set that accepts both. So that's no good. And then furthermore, if you have any like atomic update that touches that string-like overload set, you might have a whole separate problem in there. So this is going to be tricky. Maybe a better answer here is to not worry about conversions, but actually keep them as the same type. So what we could do instead is move the type where we want it into the new namespace and leave behind a spelling, a using alias, a using declaration for the type in its old home, right? Does anyone see why this breaks? I got a couple for you. First, there's forward declarations. Because we smart, we think that forward declarations save on build time. That is statistically unlikely. You are going to save on build time in cases where every single reference to that type in your translation unit is a forward declaration and nobody has included it. Good luck with that. Furthermore, by forward declaring it in usercode.h, for instance, This is now a build break for the users of usercode.h because you can't forward declare it as a class when it is in fact an alias, right? So now you've just gotten in my way. So my team will go through and take all your forward declarations and change those to includes, which doesn't actually change your build speed, and we're just annoyed and yelling at you. And then maybe this will work. Of course, it doesn't. It doesn't now because of something deeper, scarier, one of the eldritch horrors of refactoring. It's my friend ADL. Several talks I've given in the last year or two have gone into detail here, so I'll just do this briefly. In short, you can't change the namespace of a type because callers that refer to that type anywhere may be depending on the associated namespace of your type in order to find functions that also live in that namespace. So in short, for an unqualified function call, log to stood out, if there's no qualifiers, if there's no colons anywhere in that, then we're triggering unqualified lookup. First, it's going to look in F, and then it's going to look in user, and then it's going to look in the global namespace, as you expect. But it's also going to look in the namespaces that are associated with the arguments to your function. So if my function SumStringPiece is actually returning a string piece, then I get to also look in the namespaces associated with stringPiece. In the old version of my codebase, stringPiece was the primary type and lived in old NS, which happened to be the same namespace as log to stood out. And so this all works without a using declaration, without qualifications, without saying what namespace you're in. Right? But as soon as you separate a type from any of the functions in that same namespace, it's a build break. Right? So that's not great. In practice, what you're more likely to do is do it in the other order, which is we leave the class where it started, we add the alias in the new namespace, we blast through the code base to find everywhere that you're spelling stringPiece and change it to absolstringview, and also at the same time find all of the unqualified calls that depend on ADL, thank you Clang tooling, qualify those calls, and then when we're done with all of the old spellings and ADL is no longer in our way, then we move the class body into ABSL, delete the alias. Easy peasy. This is obviously imperfect. You're going to have some straggler things, right? If you actually had functions that encoded the name of the type, you're not going to hit those with a Clang-based tool or any other automatic refactoring. Your comments are probably going to be slightly out of date, things like that. We don't have perfect AI. You are going to leave a little bit of a mess doing these sorts of things, but I think on net it is still worth it. And this model of finding a way to add an alias in order to enable multiple spellings is actually sort of critical, at least to the class of refactorings that are based on renaming things. So for types, you use type alias. For class templates, you use template alias. For concepts, we spent a little while and we think this works. This is not actually an alias. Those are two distinct things, but they do subsume one another. So in like concept checking logic, they are equivalent. We're not currently aware of any way that that's going to fail when you do this. That said, I guarantee that there is nobody on the planet that has refactored a code base in anger that uses concepts. So this is untested, but in theory, this is the starting point. Weirdly, we don't have any way to rename a function. I find that kind of bizarre, but this sort of kind of works, thanks Jorg, except that's now a function object, not a function, and so it'll fail if there's overload sets or if you actually wanted ADL, God forbid. So it's not actually 100% the same, whereas the other alias forms are more high fidelity. Most of the time, you probably just bespoke do something with an inline function. It kind of works. But again, it changes behavior for ADL and some other things. And if for some horrible reason you have code that is comparing function pointers, this is definitely not the same. None of this is 100% provable. We just also know that you can definitely get away with it. Amusingly, you can change namespaces for functions. You just can't change the name, right? A using declaration works fine. Anyway, this is sort of 101 on how to add a different name for an existing thing, which is sort of key to a lot of the big picture pattern for multi-step refactoring. Most of the time, what you're trying to do is find a way to allow the before and after to coexist peacefully, right? You want two different spellings for the same name, but you want them to be the same thing. Or two different spellings for the same type, but you want them to be the same thing, right? Or you want two different spellings for behavior, or you want two different spellings for whatever, right? But you're trying to find a way to break it down so that you don't have to, in a single step, refactor every caller and every reference to whatever thing that you're talking about. And in order to smear that over time, inherently you need to be able to express both the before and after, like in a collaborative sort of like mutually allowable way. Does that make sense? Okay. We'll do another example now with behavioral change. So once upon a time, we had stircat internally, and the original implementation, for whatever reason, when you printed a double, printed a full precision representation of that double. It turns out that is fairly expensive because it is just as much work to format the last bits as it is to format the most significant bits. And almost nobody actually wants 34 characters worth of precision when they're like printing the string output for a double, right? That's kind of a bad default. And so to save both some CPU and provide a better user experience, we're like, we should really change the behavior here, but behavior change is hard. People are going to be depending on this. So you need to find a way to make, to express the intent of, I would like the old behavior, and to let that coexist while you're in the process of prepping the code base to make that change. And so we introduced something, legacy precision. And the original implementation of legacy precision is brain dead simple. There is no point to this other than to provide a different spelling. So now we use Clang tools to go through the code base and find every invocation of stircat where the expression passed into it is a double that isn't a call to legacy precision. And then we wrap all of those in a call to legacy precision. And now we know exactly where all of those are, and that the old behavior is unused, right? Aha. And so then, in a single step, you can change the unused behavior and change the implementation of legacy precision to return a string view instead of the double, right? And you preserve the old semantics while changing, like pulling the tablecloth out, right? You see how that works? In practice, we applied some heuristics when we're doing this because we wanted to only deploy the minimum set of calls to legacy precision, because if the motivation for this change was most people don't want this behavior, it would be awfully unfortunate to go force all existing users of it to stick with that behavior and leave that as a thing that is copy and pasted everywhere. So you apply some heuristics. You try to minimize the set of places where you do that. You take hopefully well-justified shortcuts and you see what, you use your best judgment. And of course, that is even still simplifying a little bit because the code base doesn't stop moving just because we started doing this operation, right? There are new calls to stircat. There are new calls to stircat on a double that are creeping in constantly. And so we have to do something, in some cases at least, to manage the backsliding. For smaller interfaces, we just don't worry about it because the rate that we can generate those changes with tooling and blast them out with tools that we've discussed in previous talks like Rosie are just so much higher than the nominal rate of backsliding on a small interface, then you just don't worry about it. For big things like stircat or the spelling of string piece versus string view, then you might have to bring to bear some bigger guns, static analysis warnings and linters and things like that. And of course, there is also the certainty that someone is going to misuse legacy precision for no reason and wind up with broken code when we make this change because Hiram's law. Yeah, that's just annoying. But in summary, you kind of, ignore the details, and roughly the plan looks something like this. Does that make sense? Of course, we don't rely on this all of the time because multi-step refactoring is expensive. And most things don't require this, right? Most of the changes that you are used to are perfectly fine, right? You can add a new function, you can add a new class, you can add a member to a class, you can add a new entry to an overload set. There are a lot of things, even on higher level structures in our catalog of design structures, there are a lot of things that you can change that are cheap and easy, most of the time. We'll get into that. And it's, of course, not just additions. There are some things you can do. You can weaken a precondition. You can define things that weren't but defined or stabilize things that were random. All of those are feasible. So I'm going to go through for a while now and look at, starting sort of at the bottom, functions, classes, templates, concepts, and look at the types of things that we can actually change and how hard they are, either as a single-step thing or how hard is a multi-step plan to execute such a change. Okay? So first off, can we change functions? There's a bunch of questions in exactly what you might want there. If it's just a rename, we already walked through sort of how to do that. If you want to change behavior, there are things that we know are mostly small, easy to apply atoms of change. You can always weaken preconditions or strengthen postconditions to allow the function to be called in more contexts or to weaken the set of things that it is likely to output, right? And of course, because those things are technically observable, there's going to be some amount of Hiram's law annoyance that comes into that, but in theory, this is all doable. It is, on the flip side, vastly more expensive to strengthen preconditions. You're going to have to go through the whole code base to find all of the callers and figure out who is actually doing that, ideally statically. And if you can't do it statically, if you can't do it through like type inference or local reasoning, you're going to have to do it with dynamic reasoning, and that's going to add runtime overhead and risk and all sorts of things. You can weaken preconditions, et cetera. Right? But these are inherently going to involve some investigation of every single call site. Doable, but expensive. Instead of changing the behavior of your type, how about we change the type signature? Can we change return types? In the case of void, probably yes, mostly yes. The only thing that I've ever actually seen go wrong here when changing a void function to return something is when callers are writing out return statements that invoke your existing void function, which is weird and rare, probably not worth losing any sleep over. And in fact, the committee, which is pretty good about not breaking people's code most of the time, we already did this once between 14 and 17. We changed emplace back to return you a reference to the newly emplaced thing. Right? We don't believe that people are returning the value of emplace back enough for us to worry about it. I think we're probably right. But if you're changing something more than void to other things, it's sometimes harder. Can we change int to int64t? Anyone think we could do that cheaply? Nobody is foolish. In the case of widening an integer type or numerics in general, no. Because the output of one function is the input to another function, right? And so a simple call chain like this is a narrowing problem, and depending on your compiler settings, hopefully this becomes a build break. So we're going to have to use some non-atomic, some multi-step refactoring approach in order to execute this change. And that might be as expensive as renaming the thing away, renaming foo to something completely different, reintroducing foo with the signature that you want, and then converting people back. All right, so you're going to hit all callers to foo maybe twice. This is doable, but it's not cheap. It's going to be a bit of work. So if we can't widen, can we narrow? Anyone think we can narrow? Everyone's terrified. Oh, Zola, maybe. And interestingly, it actually isn't any easier, but for different reasons. It is also hard. For instance, printf is demonically annoying. I cannot express how much this bothers me. It is honestly the fact that, like, one of the long-standing things that I desperately want to change in our code base is a type def that would change long to int64t. And it would break so many format strings that it was easier for us to design, implement, deploy, convert callers for absol stir format than to fix this problem, which is kind of an amazing yak shave. You also get into template deduction fails, right? You can't call std_min if the two arguments are not actually of the same type. So if I change one of these from long to int, deduction failure, right? Not great. Basically amenable to the same trick as before. You rename it away, you introduce the new thing, you identify the places that you can convert back, you pray. It's a lot of work. So changing function signatures is broadly hard. The signature of a function is going to break something, right? As a basic refactoring, it is a fairly expensive one. And that's true even in the case where your programmers are well behaved and they're just calling the function. If anyone is taking the address of your function, if function pointers are involved anywhere, then you have a whole additional level of complexity because those types become dependent, right? If you have function pointers or forward declarations in place, all bets are off, right? It becomes just more expensive. So, functions. That's what you can do, basically. Can we change types? For example, can we change between two compatible types? So I have an unordered map. Can I make that a faster hash map? Right? Can I use node hash map? Has effectively the same semantics as far as iterator and pointer invalidation goes. And unsurprisingly, this is hard. This is expensive for two reasons. The first of which is Hiram's law. Again, always. Thank you, Hiram. For instance, this test will fail because the iteration order of unordered map is fixed and stable, right? If you insert two elements into the map and you iterate through the results, you're going to get those two elements out in the same order all the time. People are going to write this test that depends on encountering those elements in that order. Hopefully it's only tests and not production code. Hopefully you're not serializing things to your database, but with a large enough usage you are. So have fun with that. For a lot more stories on this topic in particular, go see my friend Matt Koulakundis' talk on hash tables and recent optimizations tomorrow afternoon, because we have got some wild Hiram's Law stories in that talk. It is also expensive, though, because vocabulary types are not independent, right? Vocabulary types, things that pass through APIs, form dependency networks. So it isn't just that I can refactor F by changing that instantiation. I have to also refactor everything that that instantiation is passed to, right? So I have to also hit G, right? And it isn't that I can just refactor F and G. It is also that I have to refactor everything else in the codebase that calls G. And it is not just that, it is also everything else that the things passed to G are passed to, etc., recurse. Right? This can be difficult. So you can kind of do it, and we've done it, but it's tricky and expensive, and we're kind of just beating it with a hammer. Amusingly, I have been terrified of this exact example for years, and Matt Koulakundis was like, you know, let's just see what happens. I'll see how many of these changes I can commit without breaking anybody's build. And so we're just blowing through the code base, attempting to make changes and seeing what the CI results look like. And if it passes, then we'll commit it. This is not particularly robust or reliable. It's very reliable. It's not very smart. It's not very efficient, but it gets the job done. So there's that, I guess. So you can sort of do this, but it's tricky. And vocabulary types are hard. Right? This is a big part of why I say, do not introduce more vocabulary types into your ecosystem lightly. This is a big part of why when I sit in library evolution, I fight pretty hard against why do we have a second one of these for the same purpose. I don't always win that, but functionally, changing behavior or semantics or class invariance of a type is harder than a function, right? There's some things you can do to a function, right? You can weaken preconditions to a function. I don't believe that there's anything you can do to a type that isn't going to be this sort of multi-step refactoring process, right? It's doable, but it's expensive. We're going to hit everything probably once or twice. Can we change virtual interfaces? Imagine I wanted to change that int to a double. My guess is this is the cheapest you can do. And this is hitting all callers probably twice, plus all derived classes several times. Amusingly, the addition of the override keyword adds new, exciting levels of complexity to this task. Change is not easy, right? And do not get me started on your foolish warnings. There are some compiler warnings that are actively hostile to making any sort of interesting change. So I think it is safe to say this is meaningfully harder than changing just the type on a function, right? Because we have a higher level abstraction, this virtual function, we are paying more cost. And you see a sort of similar thing with function templates, much like virtual functions. You can weaken preconditions or strengthen postconditions unless there are specializations, right? And depending on how many user-provided types get rinsed through the body of your function template, it is entirely possible for all of the implementation details of your function template to be exactly necessary, right? You cannot add any additional operations because people will have absolutely implemented a type and given it only a less than in order to rinse it through your function template, right? Even if you designed everything to work on sensible values, right? Users are clever and take shortcuts. Hiram's law always works. And now we get into kind of my point here. Can we change concepts? And I will admit, in a single step, concepts are like everything else, right? If you have absolute visibility into the source of the thing that you're talking about and every usage of it, you can change whatever you want, right? Deleting your code base is always an option and can be done in one step, right? Renaming your concept or changing its behavior completely is always possible if you have small enough usage and perfect visibility. That's not interesting, though. And in the multi-step world, I do not believe that there is anything that you can do to a concept once it has escaped your control. We can rename them, I guess, but that's sort of just introducing a new name that's equivalent. So I'll go into the two things that you might do, right? In concepts, you're going to try to either weaken or strengthen the concept, right? You either want fewer or more requirements, and I will show you that neither is possible, right? Weakening is out of the question. So here's a slightly contrived example out of C++20, where we had a late-breaking proposal to change the requirements on input and output iterators from requiring copyable to only requiring movable, right? This sounds actually quite reasonable, because if you had an input iterator and you made a copy of it and you increment one of them, the old one is nonsense, right? Functionally, we should probably be treating these as move-only types, or at least requiring only move. But this implementation of wrapped iterator, for instance, is accidentally copying it. It doesn't break that requirement that you don't touch the old one. It just sort of accidentally copies it because it's an iterator. It's trivial to copy. Calling std move on it would be kind of weird, right? But code would absolutely be written again like this if we published the concept in the original form as copyable, right? So changing it after the fact to require movable would break everyone that had implemented this, right? That's not great. And anyone that passed it by value without moving it and all of those things. Yes, there was a hand maybe, but you should go to the mic. You're working on it, okay. And this is central to a lot of the last minute changes in ranges and the new iterator machinery in C++20, right? All of these things should presumably be single pass, and we recognize that, and move only is actually a better match for the behavior. But we have to do an awful lot of work at the very last minute to make this change because we can't weaken it after the fact. Chris, I think? Yeah.
So my question is, if we weaken this from copyable to movable, because copyable refines movable, where is the break here?
The break is the user that is copying it. Because
but we're not saying there's no copy here.
Was that?
We're not saying that you can't copy, we're just saying we don't need a copy.
But if the user code should be written against what the concept actually provides, right? If the concept says movable, does not say copyable, and you copy it, that does not sound like adhering to the concept, right?
Yeah, I agree with that.
Yeah, that's the crux of it.
Okay, so a break doesn't necessarily need to result in some sort of compilation error.
Depending on how checked your concept specification is, it may very well be a break, but it is also important to keep in mind that concepts are both syntactic requirements and semantic requirements, and weakening a semantic requirement at the same time still throws it out of conformance even if it happens to build, right? You do have to match what it says.
Yep, fair enough.
Okay, David.
Yeah, I mean, I think I'm asking almost the same thing, but in different words. Like, no one's calling this with a non-copyable input iterator before the change.
No one is copying, yes, before the change, correct.
You make the change, no code breaks immediately.
No code breaks immediately unless your compiler is checking the syntactic requirements.
Or you're requiring schema in some context.
Yeah, like you might get away with it, but it's a might, and I actually not convinced that you will. And as soon as the change lands in any form and someone implements a thing that does the minimum or correct job for that iterator, then you're having deeper problems.
I'm not implying it's a good thing. I'm just saying that you might get away with it.
You might get away with it. There's a lot of things you might get away with. Strengthening is also out of the question for sort of the reverse reason, right? If I had a poor concept addable that was just the syntactic requirement, if I wanted to add a semantic requirement that has to also be commutative, old types that matched string is addable under the old model, but is not addable because it's not commutative, right? You can't swap them back and forth, right? So you'd throw something else out of conformance. If you don't have perfect visibility for this type of change, the only thing that you can really do is rename the concept away and reuse the name, or find a new name and just add a new concept, right? We'll have iterator 2, or 3, or 7, whatever. And because, like I said, concepts have both syntactic and semantic meaning to them, even just the fact that it still builds does not mean it is correct, right? You might be semantically out of conformance. We also see this in type erasure for things like std function or std any, which is not surprising because type erased types are very much the dynamic runtime library version of concepts. In fact, it might even be easier to see why there's no small atom of change for concepts. We can't add an API to std function and have it go through to the underlying callable because many existing callables don't have that API, right? Similarly, we can't remove an API from std function, can't remove the call operator, because everything that is written in terms of the API that std function provides is using that interface, right? You can neither weaken nor strengthen. You can neither add nor remove. I don't think concepts and type erase types are uniquely hard in this case. For any structure that can be used as both constraint and interface, changes are going to be effectively impossible. We encountered a limited form of this with the old iterator hierarchy, where the set of tags suggested that that set was complete. Right? There was code out there in the wild that had a exhaustive switch, effectively, on the set of iterator tags. And even if we wanted to add new things like contiguous iterator under the old model, there's nowhere to put that tag without breaking existing code. And you can't remove existing tags for obvious reasons. All of which brings us to the suggestion that the higher level expressive structures scale with refactoring cost, right? If you're trying to make any sort of change, even in the concept space, just weakening or strengthening something, right? It's becoming increasingly expensive, if not impossible. And this is, I think, very interesting because this is the opposite of how everything started here. We moved away from pile of code to structured programming, and that additional structure gave us more flexibility. It gave us invariants that allowed local reasoning. But now the higher level structures have taken those invariants and spread them through your whole code base, all of your users. And so now it is no longer local reasoning, it is once again global, which is complicated and doesn't scale well. And that is also to say that the higher level structures, even though these are arguably zero cost abstractions in terms of runtime, they have meaningful costs elsewhere, right? You have saved some on expressivity, you have saved some on being able to write it or specify it more easily, but you have also painted yourself into new and exciting corners that we don't fully understand yet. For more on that, see Chandler's talk later this afternoon. To recap, we looked at the difference between traditional refactoring, the Fowler Refactorings, things that you would see in your IDE, and what I am terming multi-step refactoring. Suggestions for better terminology, very welcome. And this multi-step refactoring model covers a wider scope of things and is applicable in many, many more scenarios than the traditional single-step Fowler models. Another way of looking at it is that these multi-step methods are what we rely upon to make what others would call a breaking change. I think that is a dumb term still, because literally everything you do is going to break someone because Hiram's law works all the time. I hate the term because breaking change is not binary. It is a gradient. It is shades of gray. We've seen in this talk that changes to function semantics may be cheap in some forms, weakening preconditions, for instance, but in a strongly typed language like C++, changing the typed signature of a function is not necessarily safe. Even just widening an output type is a potentially breaking change because types are both inputs and outputs. Classes do the same, except now they're even harder because they tie interfaces together in these sorts of dependency and declaration networks. Vocabulary types are particularly expensive, and even if your type isn't vocabulary, it has inherently, like the whole reason you have types is to have invariants on your data, right? Those invariants need to hold for the lifetime of your type, right? You're going to have time concerns that are much more complicated than just the functional, immediate, imperative behavioral change when you're refactoring a function. Classes help us encapsulate, but they are harder to refactor. Templates and polymorphism generalize even further and give us more expressive power, but we pay for that with higher difficulty and more exciting ways for things to go wrong. Even simple things like refactoring a function template get really bad if you have exciting users and poorly defined specializations or interesting user-defined types. Concepts are the newest addition to all of this hierarchy, and no one has any real experience maintaining them. At present, to my mind, it does not look like concepts are amenable to change in any way once they escape your control. You can neither weaken nor strengthen them without potentially breaking users of existing code. These multi-step methods may mitigate it slightly, if you have visibility at least, or if you're just trying to rename something away. But I strongly encourage authors of C++20 libraries to be very careful. Do not publish new concepts unless you are 100% sure about them, or you don't care about breaking users in the future. Questions? Chris.
So something that I've been thinking about since you started mentioning that we can't just arbitrarily change concepts without these concerns is, well, what happens if I have a requirement in a concept and, well, sorry, I have multiple requirements in a concept and then I want to factor that into another concept post-release. So now I have another name that I'm going to add. That's technically changing the concept but keeping all the requirements and also introducing a new name. Is that problematic?
Nobody has done any of this in anger. I assume so, because of like your brief description of it. My gut says yes, and Hiram's law always wins. Like, I cannot imagine that you get away with anything at scale. If you have relatively few users, yeah, sure, but I don't think there's an easy out here.
That's disappointing. Thank you.
Yep.
Hi, I'm Roth. I just was wondering, in situations where Sphinai is being used to essentially kind of be creating implicit concepts in a library, do you see that as different and true language concepts as being harder to refactor, or are they one and the same?
Sphinai is different because it is conditioning, like, Sphinai is only one half of the concept, in the sense of it is setting the requirements on invoking this function, but it is not necessarily the entirety of the interface that that function is relying upon, if that makes sense?
Yeah, I think so, yeah.
Yeah, so like, because of that minor discrepancy, I think you have more likelihood to get away with some things.
Hey, Titus. Following up on the question that I asked earlier, I think I agree with everything in this talk except for the weakening of concepts. I think the weakening example you showed is pretty similar to the example you showed earlier with the change in behavior of the function, where you slide in the legacy precision function that does the conversion from the weaker version, initially does nothing, eventually does the conversion of the weaker version to the stronger version, and then you eventually slide it out.
Yes, if you have perfect visibility into the users of your concept.
If you have the same visibility as the example you described before.
Right, so I can do this, but if you are publishing concepts and lose visibility, because the multi-step refactoring becomes necessary either at scale or because you lost visibility, right? I can do this because we have scale, and so with visibility, scale is annoying, but all tractable. Once you have lost visibility, like, you could try to ship a tool to find everyone that was depending on the old behavior and try to come up with some way to refactor them so that they are not. That will be an awesome new research project.
But that was the same as the StirCat example.
Yes.
Right. Okay.
Right. Behavioral changes are very difficult if you don't have visibility.
Great.
Scale helps. Visibility is great. Scale is, yeah.
Hi. So the implication of refactoring is that you're kind of either finding and replacing something immediately or not long after. At what point do you decide?
I'm sorry, I can't quite hear you. Can you get closer to the mic?
Yeah. So the implication of refactoring is that you're either replacing something immediately or replacing it not long afterwards. At what point do you decide that you have tools like deprecated attribute inline namespaces? When do you decide that you want both things to coexist without immediately replacing them?
For us, I think it is almost always a matter of how many times it is spelled in the code base. If you have perfect visibility and it's only used 500 times, we'll just do it, right? You don't have to go to multi-step methods, all of these things, right? If it is spelled many more times than that, then you almost certainly are going to have to come up with a more intricate plan.
Okay.
And of course, on top of that, none of this is possible at all without tests and CI, right? Like, you have to have visibility into, does your user's code still build? Do the tests still pass? Like, have they done something super weird? So, Arthur.
Could you go back to the slide? It was about 67 or so, where you had the step-by-step for naming a pure virtual function. Yeah, this guy. So two things about this. My understanding is that if this were a concept, you could do basically the same steps to change the concept in some way. Again, as you say, this requires perfect visibility.
Yes.
But is your understanding also that if you had visibility, you could do these steps or their analogs and change the concept?
Probably.
And that first step, rename get area to get into area everywhere, even
Is
if you have
a
visibility.
very expensive thing on its own.
Okay, that if you have scale is still very expensive.
Yes.
You don't have a good way to do that at scale.
Yep.
Okay.
I think I got time for one more.
Hi, I'm Stefan. Am I right in thinking that all of this essentially means that there is a continuum between library features and how they're implemented and the cost to an organization using that feature at scale? So taking, for instance, a strong type library that generates lots of templates, and you find that you want to refactor something in that library, that suddenly doesn't feel funny.
Right. Definitely go to Chandler's talk. Yep. Thank you all very much.